The first next lesson is electromagnetic induction. The word induction shows that there is an induced current or induced EMF in this whole lesson, which is based on the principle of a generator. We have learnt about motor. Motor was purely based on Fleming's left hand rule, where in a motor electrical energy gets converted into mechanical energy. And the water starts pumping up. That's based on Fleming's left hand rule. Whereas here generator is about getting mechanical energy getting converted into electrical energy. Mechanical energy getting converted into electrical energy. That is, when the coil is rotating, you allow this to rotate, that's an induced current. That's how electricity is generated in a generator. So then, can you see that the coil is rotating, and you think that the magnetic field is uniform between the north and south pole because there's a north pole here and south pole. You think it's uniform, but as the coil is rotating at every angle, the B ds cos theta, the theta is going to vary, the angle between the magnetic field and the ds vector. As I told you, the normal vector to the coil is like this. The magnetic field is from north to south, and so as it rotates every time the angle is going to be different. Say for example, so in this case you see the cross, the view from the side, that is this side of the coil here is seen like that, which means the coil is like, you can't see the full plane of the coil, you can see only one side of the coil, one wire of the coil. That shows that maximum flux will pass through because the normal vector of the coil is ds vector, which is in blue color. Can you see that the ds vector which I have marked here? And so then the magnetic field and the ds vector parallel to each other, so maximum flux will pass through. So the flux is maximum in this case. Whereas here when the coil is like this, this end is here and it's a plane. Can you see the full plane of the coil? You see that the ds vector, which is normal to the coil, and the magnetic field are perpendicular to each other, or in other words, the magnetic field lines is on the plane, which shows the theta is 0. This shows the theta is 90, I am sorry, in this case the theta is 90. The angle between the ds vector and the magnetic field are 90 degree, and so cos 90 is 0. So the flux is 0 in this case. So the flux is 0 here, the flux is maximum here, in this case the flux is maximum, and here depending on the angle, theta is 45 degree or theta is 30 degree, the flux will vary because flux is B ds cos theta. So then therefore it is always ds vector is normal to the coil, So you have the ds vector is always normal to the coil. So then this you know that it's varying magnetic field, due to which the flux keeps changing. The delta phi d phi keeps changing for every position of the rotating coil, because of which an EMF gets induced, and induced current flows through, because of which an EMF is getting induced. It's called induced EMF E, induced EMF, which will be equal to rate of change of flux. Let's look at Faraday's law. His law states that that's the varying flux, flux is changing continuously in the coil as it rotates. The varying flux linked with the coil produces an induced EMF in the coil. This induced EMF is directly proportional to rate of change of flux. How much ever the flux is changing, that much induced EMF will be produced. If this flux is a constant, obviously if the flux is a constant, can you see phi is a constant, d by dt of a constant is 0, the EMF will be 0. So thus the EMF can be 0 if flux is a constant. So EMF lasts only as long as flux is changing. That's the third law. In general, you can represent the Faraday's law as E is equal to minus n into d phi by dt, where the minus sign shows that the EMF induced opposes what has caused it. What has caused it? The change in the flux. So there's a negative sign to show that. So then let's go look at Lenz's rule. He talks about the same Faraday's law, where there's an induced EMF because of the varying flux. There's an induced EMF slash induced current, and this induced current's direction is in such a way so as to oppose what has caused it. So then the induced current is going to oppose what's caused it. Let's understand this better. Let's take a coil here. Let's move a bar magnet, a north pole of the bar magnet towards the coil. You see, when I'm moving the bar magnet towards coil, the magnetic field lines is always from north to south. It comes out like that. Yeah. So then the magnetic field, the delta phi, will increase in this direction. There's an increase in the flux in this direction. As you bring the magnet closer to the coil, the flux increases, the field lines increases closer to the coil. So there's an increase in the flux in this direction. And basically the induced current has to oppose this. So there has to be a flux in this direction to oppose this flux. Okay, so then therefore to produce a flux in this direction, keep your right hand thumb rule, the thumb pointing to the direction of the flux that you want to induce. The flux that you want to induce in this direction. So the curled finger, you just keep your hand and see with the nails here. Can you see the nails will be here? The curled finger clearly indicates the direction of the current. If this is the direction of delta phi, the curled finger can indicate the direction of the current, induced current. So it's downward. So it's downward. So then the direction is, of it is downward. So when it goes like this, it's going to be like this, downward, 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 which shows that this current, the coil is flowing anti-clockwise. You can say the coil is flowing anti-clockwise. The nails are seen outside, it's always anti-clockwise, okay. So thus the current in the coil is anti-clockwise, and at that instant, because the current is anti-clockwise, this end behaves like a north pole and this end behaves like a south pole, and it starts repelling the magnet to oppose what is causing it, so that it will not come closer, it will go away. North pole is trying to oppose. So then so this is what happens, and you understand that say this is a single coil. If supposing this is a single coil and you have a galvanometer connected to it, it will be a lot more clearer. A galvanometer connected to it and a north pole is being brought nearer. The same rule applies here also. There is an increase in the flux in this direction delta phi, because therefore I need to induce a delta phi in the opposite direction, for which you place your hand pointing to the direction, the thumb pointing to direction of delta phi, and the curled finger. So therefore the current flows here anti-clockwise. So the current flows anti-clockwise, and comes like this, and the galvanometer will show deflection in this direction, rightward. The needle will point rightward. So thus you understand that. Or next is supposing the coil is here and you have a north pole which is going away, which means the north pole has to go away from this. So when the north pole is going away, you still know that the north pole is here, the magnetic field's direction is only like this. There is no doubts, because it emerges from north, and so then the direction of the magnetic field here is like this, and the delta phi is this, but it is decreasing because I am moving it away. It is a decreasing delta phi, whereas here it was increasing delta phi. When it is increasing, I am inducing a delta phi in the opposite direction. When it is decreasing, I try to not allow the decrease. I do not want to allow the decrease, so I am inducing a magnetic field delta phi in this direction to counter the decrease. So I keep your thumb pointing to the direction, like this, and you see the curled finger is curled inward, you can't see the nails, which shows that the current is flowing clockwise. The current is flowing upward, clockwise, upward, clockwise, upward, clockwise, upward, So therefore in this case the current is flowing clockwise when the north pole is moved away. With regard to a single coil, let us do the same thing. With regard to a single coil where there is a galvanometer connected to it, when the north pole is moved away, the same thing happens, is moved away, still the direction is like this, but there is a decrease in the magnetic field, delta phi, there is a decrease. Whenever there is a decrease in the magnetic field, I try to induce the magnetic field in the same direction so that the delta phi remains a constant. And for this I keep my thumb, I know that the current is going to flow in clockwise direction. You keep your hand, clockwise, current flows like this, like this, like this, like this, like this, like this. And so the galvanometer shows a deflection in this direction. So I am sure everybody has understood this, how it works in a solenoid, how it works in a single coil. Okay, what happens when the south pole, okay, let us take the same coil, let us move a south pole towards it. And you know that in south pole it's always direction of magnetic field is going to be from north to south, so it's going pointing inward like this, okay. So you are going to have a flux like this. at delta phi, which is going to increase because the magnet is being brought closer, so there's an increase in delta phi. To counter this increase, I should induce a delta phi in the opposite direction. So pointing your thumb in this direction, you keep your hand, you notice that your folded fingers are inward, which means clockwise, clockwise upward, clockwise upward, you know, like this. And so then you know, in this case the near end behaves like a south pole and this behaves like a north pole. So in order to repel it, because it does not want it to come closer, it has to work against what's happening, what's caused it. So it's moving the magnet away. So then this is the same case in the case of a single coil too. Supposing you have a single coil and you have a galvanometer attached to it, and you're moving the south pole towards it. You know, the same rule applies, that is the magnetic field's direction is like this, the original magnetic field, delta phi change in the flux is like this, because it's from north to south. You know, considering that the delta phi is like this and it is increasing, and to counter it I have to induce a magnetic field in this direction. So keeping the thumb, you know that the direction is clockwise. So then it's clockwise, and so the current flows like this, like this, like this, like this, like this, and the deflection is like this. So, so it's quite opposite to what happens when a north pole is moved towards. When the north pole is moved towards, it was anti-clockwise direction. When the south pole is moved towards, it's in clockwise direction. It's very, very simple. But don't memorize it, try to understand what's happening. Now, the same coil, the south pole is moved away. The same coil, the south pole is now moved away. South pole, the direction of the magnetic field is always like this. But delta phi here is decreasing because it's moved away. So in order to counter the decrease, I have to supply some more delta phi in the same direction. So then therefore thumb pointing in this direction, nails is here, at the curled finger with all the nails seen. That's the direction in which your current has to be, which is anti-clockwise. So how do you mark anti-clockwise? Sorry, how do you mark anti-clockwise? The coil, it's like this, can you see? Like this, and anti-clockwise, you have anti-clockwise, like this, downward. You know, so then that's what is happening. And if it is in the case of a single coil, so which is quite opposite to what is happening here, it goes clockwise, here it is, when it's moving towards it's clockwise, here moving away it's anti-clockwise, but we are understanding everything I'm doing. And you have a galvanometer connected to this, and you want to check for a single coil, the south pole is moved away, and you know that the current has to be anti-clockwise from the same principle. Yes, because the magnetic field's direction is like this, the delta phi changes in this direction to counter and it's decreasing in this direction. That's the main point. I cannot allow a decrease, so I have to produce an magnetic field same direction. When I point my thumb, I understand that it's anti-clockwise. So then what happens here too, the near end behaves like a south pole. No, here it behaves like a north pole. The near end, because it's going away and it has prevented from going away. So then therefore this end behaves like a north pole in order to attract it, and the far end behaves like a south pole. It will try to attract, oppose. Here it was coming closer, so therefore the near end behaves like a south pole to repel it. Here it was going away, so then north pole is going away, it should not allow, so this behaves like a south pole so that it can attract. So these are the things that you should understand, okay. So then, and thus what happens is, in a Lenz's rule you notice that you are initially moving the magnet, which is mechanical energy, which is getting converted into as a electrical energy, this induced current, electrical energy. And this electrical energy, the current that is induced, produces a north and the south pole to repel or attract on the coil itself. So then it's a magnetic energy, that's a new term, okay, magnetic energy, which in turn repels the coil, so again a mechanical energy. So then this process continues, and so it's conservation of energy, it's adhering to conservation of energy. Lenz's rule adheres to conservation of energy. So thus you find the directions very, very important. I hope everybody understood this. So then let's look at some more sums in the book back that's given. So then there is a coil here, and there is a wire, a rectangular wire which goes like this and is connected to this. This is named as P, this is named as Q, this is named as R. Now I am bringing a south pole near this coil. You know, if I bring the south pole near this coil, I am doing the conceptual. Once again, when I am, south pole's direction is always north to south, you all know that, north to south, sorry, pointing this direction. So therefore, I know that there will be a delta phi, there will be an increase in delta phi, because I am moving the magnet closer, there will be an increase in delta phi. To counter it, I have to induce a flux in this direction. So keeping my thumb pointing this direction, I know that the current's direction will be like this, which is nails are not seen, therefore it's clockwise. So I understood it's clockwise. So I'm just doing clockwise, yeah, clockwise is upward, clockwise, 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 continue, continue, continue clockwise. And in the outside loop, it is flowing from QRP, anti-clockwise. If your question is about the outside loop, it's QRPQ, which is actually anti-clockwise. Even though in the coil it was clockwise, this solenoid was clockwise is the induced current, but the outside loop is a question where it is becoming anti-clockwise. So this is the direction. So that's how tricky the sum can get. Okay. So next sum that we discussed today is like a coil was there, and you have a P, a Q and an R, and another coil is there, and you have the direction here marked as X, Y and then Z. You are moving a magnet, the south pole here, north pole here, in this direction. Okay, so then in between you are standing and moving it. You are standing here and moving the magnet to the left. You know, when south pole is moved towards, what is happening? You can always refer back the conceptual, but I am doing it again so that you become very, very clear. So the magnetic field is always from north to south, so the delta phi is going to be in this direction because south pole is moved towards, because it's like this. So therefore, my magnetic flux is in this direction. There is an increase in the flux in this case. There is an increase because the south pole is moved towards, and to counter that I need to have a flux induced in the opposite direction. So then when I keep my thumb, I get to know that it's clockwise. The current is flowing upward, it's clockwise, clockwise, clockwise. You know, the current is actually getting induced clockwise. It starts getting induced from the end Q actually, because that's the closest end. So from the end Q it starts getting induced. So when it gets induced it's clockwise, and when it comes out also it's clockwise, no issues. So it is QRPQ. That's the direction the current starts flowing, which is clockwise. Okay. But what happens to the second one, second coil? Here the north pole is moving away. As you move this magnet to the left, the north pole is moving away. So you know that the direction in which the magnetic field line is always from north to south. So the magnetic field, from north, yeah, it's like this, correct? And so then the magnetic flux direction, I'll mark it like this. This is the direction of delta phi. And is it decreasing or increasing? It's moved away, so it's decreasing. To counter the decrease, I have to produce a magnetic field in the same direction, delta phi. And to produce, keep the thumb, you find that the current is flowing in anti-clockwise direction. Keep the thumb pointing to the purple color arrow, a curled finger indicates direction, nails outside shows the anti-clockwise direction, and so then the current is going to flow, and from Y it's going to flow anti-clockwise direction, downward, anti-clockwise, downward, anti-clockwise, downward, you know. So it comes out like that and flows from XZ, X. Yeah, so the current flows from Y to X, right? Y to X. Okay, we can say that this starts from the Fx starts from X because it's closer to the magnet. So will let's write the induced direction to be X, Z, Y, X. So then it is actually from x to y, in other words x to y, if they ask you depending on the question MCQ, okay, it flows from x to y. So that's about it, and the direction on both the sides are known. Such a beautiful sum. So let's go to next question. Is there is a coil like this. It's a three-dimensional view of the coil, okay, and you have this end connected to the positive terminal, negative terminal, and you have a key here, okay, and this is a circuit, and there is another coil here, and this is like a three-dimensional view. Can you see the axis goes like this, and this goes like this and comes out like this, which shows that the outer side is here and here. Sanjay, you asked me this doubt. So then it's very clear which forms the outer side, okay. So then therefore can you see the current is going to go like this, and the current is going to go like this in this, which is going so here the question is about the key just closed. So we are closing the key. What is the meaning? We are switching on. Just the moment when you are switching on, the current rises from 0 to 5 amps, say for example. That's when there is a change in the current Di. Only when there is a change in the current, the magnetic field will change. If the current, okay, the current carrying conductor produces a magnetic field, everybody knows that. But the change in the current is what is going to give you a change in the magnetic field, which will result in change in flux d phi. The change in flux is what is going to produce an EMF. So all of these are interconnected. So the current has to change, if the current is going to remain at 5 amps, there is no induced EMF. But when the current is going from 0 to 5 amps, there is a rise in the current is increasing by Di, which produces a change in the magnetic field, and so then the d phi it's switched on, so it's increasing. So let's to understand the direction of the magnetic field, let's consider this to be flat circles, okay. The current is flowing clockwise. The second loop is here. The current is going clockwise. You keep, let's apply the right hand thumb rule, the curled finger pointing the direction of the current, the magnetic field will be inward. Therefore, the d phi, the delta phi that I am talking about here, d phi or the delta phi, which is increasing, which is also in inward direction. It's increasing in inward direction. Cross means inward, point means outward, okay. So then therefore I have, since it's increasing inward, I have to induce a magnetic field which is outward at delta phi, which is outward. So then I keep the thumb pointing to the direction outward, pointing to my nose. The curled finger will indicate the direction of the magnetic field, and so the curled finger is curled leftward, which is anti-clockwise direction. The current induced in the adjacent coil has to be anti-clockwise direction, so that the flux will be outward in order to counter the increasing flux inward. So the current in the adjacent coil must flow, supposing the direction has been given here, the alphabets such as X, Y and Z is given. I understood that the current here, the flat, I took it as flat surface, and inward and outward magnetic field is easier for me. So then therefore I found the direction to be anti-clockwise, so then the current flows in this direction, which is X, Y, Z, X. That is the direction in which the current is flowing. X, Y, Z. They have left with X, Y, Z. Whatever is your MCQ options, you can use that as your answer. So I hope you understood. So if you don't understand, just play it again and again. This is about, when you are switching on, it is about the current increasing, so the delta phi is increasing, flux is increasing. When you are switching off, it is quite the opposite. When you are supposing switching off, so let us study the same case for switching off condition. Switching off, it is going to come down from 5 amps to 0 amps. It is not given in the question, 5 amps to 0 amps. So there is a decrease in the current, and so then there will be a decrease in the flux. There will be a decrease in the flux. And which direction is the flux decreasing? Again, the same direction as the magnetic field. The magnetic field direction is inward, so there is a decrease in inward direction. And to counter this, whenever there is a decrease, I try to produce a d phi in the same direction to counter the decrease. So which has to be inward. So then if I have to get a magnetic, the flux change in the same direction, which is inward, thumb pointing to direction of the flux which is inward inside the paper, you see that the clockwise should be the direction of the induced current. If the same question was asked, I would write clockwise, which is adjacent to the same sum. You see the same sum where the question is about switching off. If it's about switching off, it's about switching off. The current's direction reverses in the adjacent coil, you see. So that's all. This is for your understanding. If they change around the question, you should still be able to answer. Okay. So let's go to the next question. The next question is you have a coil like this. Okay. Again, it's a three-dimensional view: X, Y, Z, and there's a coil here, which is this side is connected to a battery and a variable rheostat. Okay, that side goes like this, and connects to a variable rheostat. Okay, something like that. It's there in the textbook, you can see. Okay, so then I'm going to draw an axis like this to show that this part is outside and this part is outside. So then let's continue with the sum. The rheostat setting being changed. See, when the rheostat setting is changed, obviously current is going to change, resistance is going to change, which is going to, they are not saying increasing or decreasing, change, that is all. The rheostat is getting changed, the current is going to change, and so then that is going to, the current here is going to change and it is going to increase or decrease the magnetic field. One second. It's given that the rheostat is moving in this direction. We are moving the rheostat in that direction. Okay. So, can you see that the rheostat is moving in this direction? They have given that, and that shows that the current is increasing. Okay. The current is increasing because resistance is decreasing. As you move close to the other end, resistance is decreasing, so of the rheostat, and so the current is increasing. When the current is increasing, which is the di, a change in the current is increasing, the d phi will also increase. But in which direction? The delta phi is increasing in which direction? Look at this curled finger pointing in the direction of the current here. The magnetic field B will be pointing outward. So it's a point means it's outward. The magnetic field at the center will be pointing outward. So d phi is also outward. And is it increasing? I said the current is increasing, so d phi is also increasing outward. So in order to decrease it, I have to induce a delta phi which is inward. If in the adjacent coil, I have to induce a delta phi which is inward. For delta phi to be inward, keep your thumb pointing down and away from your nose, or into the paper, into the plane of the paper. The curled finger, which is clockwise, indicates the direction of the current here. So it has to be in the direction z, y, x, whatever. Okay, so that's the next question. So it's very important how the rheostat is moving, how the current is increasing, because the resistance is decreasing as you move it that side. So please note down that point. Okay. So let's go to the next question. As supposing you have a cardboard of which you're winding up a solenoid, a coil of wires. Okay. So this is there's an adjacent coil. You've done this experiment, you've heard of this experiment, Faraday's experiment in 10th standard, you would have come across this. So you have a coil like this and you have a no key here. Okay. And can you see the polarity is positive, this negative current direction we have to see. Okay. So there is a direction which is x, r, y has been given at these points. We have to find out which direction is the induced current. Okay. Now, if you see, there's no magnet here, but we know you know that when you switch on and switch off, there is a change in the current due to which also there is a change in the flux, not just a magnet. You know, so the mugging up of north and south pole and all will not work. So you should basically understand the concept well. So then here, due to the what are we doing? We are releasing the key, which means we are switching off, which means from 5 amps, say for example finite amps, some finite amps is coming to 0 amps. So the current is decreasing, delta I is decreasing, so delta phi will decrease. Yeah. So this delta phi is decreasing in which direction? Let us see. Okay, for me, it's easy for me to understand it as one single coil, and you know, the current is flowing. Initially the current was flowing in this direction. It was on, it was flowing in this direction. Now it's being switched off, but at that moment also the direction is the same. So supposing you have one single coil, let's draw it as one single coil and a flat surface. Okay, and you have a positive here and negative here, and of course you are switching off, which means you are opening. At the moment when you are switching off, the current is decreasing. In which direction? It's the direction of the current. The current will decrease in the same direction. Yeah, whether it's increasing or decreasing, the direction of the current is the same, but it's just that it's decreasing. Okay, so then therefore you know, the magnetic field is actually outward. If you keep curled finger, B is outward, and it's the delta phi is going to decrease because delta I is decreasing, the change in the current is decreasing. The delta phi will decrease, and which direction? Outward direction. So it's decreasing. I will not allow the decrease, so I'll induce a delta phi in the same direction, outward. So you have to induce the same outward direction, delta phi. Keep your thumb pointing to the direction of outward, that is pointing nose. A curled finger, the curled finger indicates the direction of the magnetic field that has been induced to the adjacent wire. Yeah, and which means the curled finger, this is the direction of the induced current which has got to be induced. So then I will going back to this, I understand that the induced current in the second coil would be anti-clockwise. So it's like this, anti-clockwise should always point downward. So then just for consistency, anti-clockwise is downward, anti-clockwise, anti-clockwise, anti-clockwise. So it is, the current flows in XRY direction, XRY direction, or the current flows from X to Y, in other words. So that's how it works. I'm sure everybody understood. The advantage of considering it as flat surface and understanding the direction of magnetic field really helps me in doing the sum. So that's how I do it. You can also do the same thing. So the last question, oh no, not the last. Okay, so then this is the question. I do not understand the question here very clearly because I do not have the textbook. It's just some version of textbook I have, where there is a wire like this. I think this is a wire, and there is another wire like this. Oh, okay, these are two different wires. One is a circular wire and one is a straight wire. The straight wire, there is a current which is going. The circular wire, there is no current. Okay, so there will be an induced current in the circular wire. Therefore, point your thumb in the direction of the current. The curled finger will with the nails here will point the direction of the magnetic field, magnetic field. So the magnetic field here, you see, will be the magnetic field lines is in the plane of the loop, is the same plane as the loop. Of the circular loop. If you see the circular loop, the magnetic field will be in the same plane as a circular loop. Or in other words, the magnetic field I am going to draw like my finger. The magnetic field's direction is in this direction, and the ds vector is in this direction. Can you see? The normal to the coil is pointing outward, above, you know. So then therefore BDS, flux is BDS cos 90, and therefore there is absolutely no flux, flux is 0. There is no change in flux, so no EMF and no current, no EMF and no current. So that's the sum, and there's one more sum which will be twisted in your exams. Okay, they will say that here they said that the current, okay, here they said the current is decreasing, current is decreasing. I didn't care, because whether current is increasing or decreasing, in this direction, the direction of the current is just this, and if I point my thumb anyway, the curled finger, magnetic field is going to lie on the plane. That is, the ds vector is going to be perpendicular to the magnetic field. Anyway, there is no flux. But the question will get twisted in the exam, where they will talk about a steady current. A steady current through this will induce a magnetic field. Yes. There will be a magnetic field around it. Yes. Yeah, there will be a magnetic field around it. Yeah, you know that. But the thing is, the steady current will not cause a change in the flux. Magnetic field will be uniform. There is no change in the flux, so there is no EMF. So that is an extra sum which they will ask you in exams. Okay, let us go through the second sum in your textbook. So let us look at the sum where there is a uniform magnetic field. There is a uniform magnetic field like this, and there is a small area like this, like a thread, which is a closed thread, and they have named it as A, B, C and D, and they are going to make this into a circle, which means they are going to increase the area, See, as you increase the area, see, when it is small, only few lines were passing through. When you are increasing, more lines are passing through. So there is a change in the flux which is increasing. So delta phi is increasing. Area is increasing, delta phi is increasing. In which direction? In the direction of the magnetic field which is pointing inward. So the delta phi is increasing inward. Okay, this is the, okay, I should not write all this in purple. So I should write it in black. Area, delta phi is increasing and it's inward, because this is all existing, and to oppose this increase, I have to have a magnetic field be delta phi outward. To counter this, I have to have a magnetic field outward. So point your thumb outward towards the nose, you see the curled finger which is anti-clockwise direction will be the direction which the current is getting induced. So the direction is anti-clockwise, which is DCBAD, whatever. DCBAD, or your textbook answer says ADCBA, it does not matter, ADCB, yeah, you can continue like that. So all the same, it's all the same. So then don't worry, so it's ADCB is the direction that shows it's anti-clockwise, as simple. So what happens in the next sum is there's a uniform magnetic field dot which shows that it's pointing outward, pointing to the direction of your eye. That's a magnetic field's direction. And you have a bigger circle here which is being made into a smaller loop. So there is a decrease, in area. The decrease in area will decrease the delta phi. The delta phi will decrease. In which direction is it decreasing? The direction of the magnetic field, which is outward. It's decreasing outward means I'll supply a flux in the same direction, outward, because it was decreasing to it should not decrease, so outward. So delta phi outward shows that the current again in this smaller wire has to flow, the wire, whatever wire, bigger or smaller, has to flow in anti-clockwise direction. So then again I know it's anti-clockwise, let us name the alphabet. The alphabets that's given is in the circle, this is D, this is C, this is B and this is A. The current has to flow anti-clockwise, ADCB. So therefore that ADCB will be the direction in which the induced current would be, ADCB. So I hope everybody understood. All these sums are all these things are very important conceptuals. Please rewind and go through it once again. Okay, so that is the first part of the lesson. The second part of the lesson is about the EMF induced in a rectangular coil moving in a uniform magnetic field. Suppose you have a uniform magnetic field like this. Supposing you have a uniform magnetic field like this, and you have a rectangular coil which is moving with the velocity v. You know that as this let's call this as length L. Normally this is length and this is breadth, right, in a rectangle, but we will call this as length. That's not going to change, but the component that's going to change is this. Let me mark it in green color, this x. As you move this, the portion of x which is going to be within the magnetic field will change. The rectangular coil moves, x keeps varying. The variable, x is a variable. So x is a variable. Because this is varying, and can you see that the flux will increase as you move the coil, the total number of field lines through the coil is increasing. So more number of magnetic field lines will come, if supposing this position comes to this position, you know, more flux will be there. So the flux is increasing, as you can see, the delta phi is increasing, due to which there will be a current induced. Okay, so the delta phi is increasing, and in which direction is it increasing? It's going to increase the direction of the magnetic field. The direction of magnetic field is pointing inward, so delta phi is increasing in the direction of the magnetic field. There has to be an delta phi to counter this in the opposite direction, which is outward. Because this is inward, it's increasing inward. So for the delta phi to be outward, if you keep the thumb pointing outward, pointing to your nose, the current has to flow in this in anti-clockwise direction. That is the direction of the induced current. So that's what is actually happening, and you should elaborate that in your test paper. So that's anti-clockwise direction is where the current is flowing. So then to oppose the change, okay. Now let's go to the derivation. To find the EMF, E is equal to minus d phi by dt, because it's only one turn. So E is equal to minus d phi by dt. E is equal to minus d by dt of flux is b dot ds vector, which is b ds cos theta. So E is equal to minus d by dt of b into ds area vector into cos 180. Why? Because angle between the coil and the magnetic field. Magnetic field is inward and normal to the coil is outward. Now can you imagine pointing to ice? So then therefore angle between the magnetic field and is inward, and the outward pointing to ice, inward and outside the paper is 180 degree. Therefore theta is 180 degree. Well, cos 180 is minus 1. So it will become E is equal to d by dt of b into ds. Okay, this is into, let's not put into, it's self-explanatory because it shouldn't be misunderstood as a cross product. So ds is what is area here. The area in this sum is b into Lx, length into the variable x is my EMF. What are the constants? Magnetic field does not change. The length L does not change. The length here is this L, not this. This is a variable x, as I said. Okay. So then what is going to change is only x with respect to t, and dx by dt is v. Thus the EMF induced is BLV, BLV. That's the EMF induced in a rectangular coil. And next is EMF, induced EMF. It's EMF induced, okay? EMF induced, yes. EMF induced or induced EMF? EMF induced in a rotating rod. Rotating rod. Supposing you, so you have a uniform magnetic field pointing inward. Cross is always pointing inward. A dot is pointing outward, okay? So then you have a rod. Can you imagine a rod which is being fixed here and this is getting rotated like that? Yeah? At any instant it would have come here, making an angle theta, and this becomes the area of a sector. And the area of a sector, as you all know, area of a sector is theta by 360 into pi r square. yeah, and pi and 360 can get cancelled by 2. So theta by 2 into r square. But you should know that this is the length of the rod. This is the length of the rod, which becomes the radius. R is equal to L in the sum. So you replace theta by 2 into L square. So that is my area of a sector, or ds. Ds, it's going to be ds, okay. 1 second, power is getting low. Yeah. So that's my ds vector, okay. Now I'm going to substitute this in the formula. Okay, E is equal to minus d phi by dt, which is minus d by dt of B dot ds, B ds vector. The angle between the magnetic field and the ds vector is 180 again, inward and outward. So B ds cos 180, cos 180 is minus 1, so this and this get cancelled. D by dt is B into area. Area itself is theta by 2 into L square. What are all the constants? The magnetic field is a constant, length of the rod is a constant, 2 is a constant. So d theta by dt will get you omega, angular velocity. So B L square omega by 2. Okay, I won't leave it like that. I know that linear velocity is r times angular velocity. When you run straight, you can run faster than when you going around. So angular velocity here, linear velocity here, this is more. So V is equal to r omega. So omega is equal to V by r, which becomes V by L because it's the length of the rod. Substituting here, B L square by 2 into V by L. L and L get cancelled, half BLV. Easy to remember this formula because that was BLV. That was BLV and here it's half BLV. It's easier to remember, and that's advantage. And can you see the area vector is normal? Yeah. And the flux through this area is going on increasing as you move it. Okay, so that's about it. So that's half BLV. Okay, so half BLV. Next is they might ask you to write about a motional EMF. Motional EMF, the word itself is clear, is an EMF induced due to the motion of a coil or a motion of a rod. EMF induced due to motion of a rod basically. And a coil, you can write the same derivation here because the rectangular coil consists of a rod. This is rotation of a rod, it's not motion of a rod. Okay, this is rotating rod. You can't write this. You can write this derivation because a coil consists of a rod. Can you see a rod here or a rod here? The purple color is a rod. So then therefore EMF induced due to the motion of a rod in a magnetic field is known as motional EMF, as you can see. And you write the same derivation and you write this is motional EMF. But the only point you should know in this extra point you should write in motional EMF is you have a rectangular coil, yeah, and you notice that we consider AB to be the rod. Let's consider this AB to be the rod, which is the length part, okay. And you know that the charge particle moving in a magnetic field undergoes deflection. According to the previous lesson I taught you, when an electron enters the magnetic field, it goes down. When a positive charge particle goes up. So then therefore this rod consists of negative and positive charge, where all the positive charge gets accrued here on the top and the negative charge gets accumulated here, thereby creating an electric field in downward direction. This is a very important question. The direction of the electric field will be downward, and the electric force will be equal to the Lorentz force, magnetic Lorentz, QVB, and electric force is Q into E will be equal to QVB. Okay, this additional points you have to write when they ask you about motional EMF, but you can still derive that EMF is equal to BLV, which we did. The same derivation can be continued, but except that the definition that the motion of a rod, motional EMF means an EMF induced in rod due to the motion of the rod, or in other words a coil, because coil constitutes a rod. The only extra point you need to add is the electrons in the rod moves down, electrons positive charge in the rod moves up, thereby creating an electric field from top to bottom, A to B, which will be equal to the electric force, because magnetic force is what is created it, Lorentz force is what is created the electric force, and so then the force are equal, okay, just for you to know, okay, that's all. So that's an motional EMF where you write the same rectangular coils derivation. The next derivation is you have a north pole here when you have a south pole here, you have a coil which is rotating. I taught you this. This is normal to the coil, this is magnetic field, and there's an angle theta. At any instant, theta is the angle. And you know that angular velocity is theta by t, so theta is equal to omega t. You should remember this in this case, because you have something called an angle which varies, not unlike here theta is 180. Here theta is some value at any instant. So you take this and write E is equal to minus d phi by dt, which is E is equal to minus d by dt of b dot ds vector, and it's actually minus d by dt of b ds cos omega t, because it's not 180, the angle here is omega t. This is the point you will forget. So now take all the constant out, b is a constant, the ds is nothing but L into b here. This is length and this is breadth. According to my last lesson, I taught length and breadth, L into b is area. So you can write it as A. And cos omega t differentiation of, there's a minus outside and there's a cos omega t is differentiation, which will be minus sin omega t into omega. So then it will become plus and a b a omega sin omega t. And supposing the coil is n number of turns, this is what is the induced EMF's value here. For one single turn, if it has got n turns, I have a weird way of remembering the formula. I will include an n in this formula and say it as ban omega sin omega t. Ban omega sin omega t. Just to have, because my memory is very poor, I need to recollect. How do I recollect? EMF in a rectangular coil is BLV. The EMF induced in a rotating rod was half BLV. And the EMF induced in a rotating coil in a magnetic field is ban omega sin omega t. You know, so then it's easier for me to remember the formulas in this kind of ways. So I want my students also to stick to the same way, so that if you have a memory issue, you won't struggle in the exam. Okay, so then actually this rotating rod, because of this rotating rod, there will be an current that is getting induced current, and this is the principle of a generator too. This is the principle of generator. This is how the generator is going to work. Okay, so keep that aside. So this resembles E is equal to E naught sin omega t. You will learn about the E naught sin omega t. You know that the EMF can be a sinusoidal function, so it can be represented where this is E naught. At any instant of time, it's E is equal to E naught sin omega t. This is the expression. And E naught coincides with ban omega. So then ban omega is the maximum EMF. Can you see according to the graph the maximum EMF? So the maximum current I max that is induced. They ask you in the calculation, it's E naught by the resistance R in the circuit. So in other words, it's ban omega by capital R. That's how we find the maximum current induced in a generator. The same derivation we will write even in generator, but for now this is how induced EMF is in the rectangular coil. So let's go to the last point of the day. We are going to calculate what is power. Power in a rectangular coil which is being with induced power. Okay, so power itself is rate at which work is done, and work done is force into displacement by time, and displacement by time is velocity. So power therefore is force into velocity, and this is about a motional EMF. It's about motional EMF, the power in the motional EMF. You know that the force of a rod, this motional EMF is about a rod, and so the force on a rod is BIL, Bill. From last lesson you all know. I taught you the Lorentz force of a rod, where this is A, this is L, and then Nial is the total number of charge. Considering N is the number of charge per unit volume, E is the charge, area of cross section is A, L is length, Nial is the total charge, and the Lorentz force F is Q dot V cross B for a charge particle, whereas here is a rod where Q is itself is Nial into V cross B. And you notice that NEAV is Naividar, which is BIL. That's how a force on the rod becomes Bill into V. The force is Bill into V is power. You can write I as E by R, V by R. I is equal to V by R. The whole lesson V becomes E, potential is EMF, into L into V. And EMF of a rod, you know, is BLV, yeah, BLV. So B into BLV into V into L into V by R shows that it's B square L square V square by R, which is BLV the whole square, BLV the whole square by R. So these are the formulas you should memorize, because at any instant they'll ask you the power. So this is very, very important. Till here you be clear, so that I can continue whatever I want to take in the next class. Please go through my video, become clear kids.